Okay, so maybe one more time here. So again, if you look, I'm way up here above in the 40s and 50s. You can look up here just below 50 here, 49 point whatever that is. You can find out that there's a piece of that graph that's way up here and goes up there forever. And then you had those other two parts where the 3 and the 4 were the asymptotes down at the bottom. So way down here, if you zoomed in on these, you could see that when you get in here, these always stay right between the 3 and the 4 as well. So that there's your other asymptotes right there. Now, it would appear though that this one approaches from over here. This actually crosses the x-axis, goes above, and then it comes down. But I think the one on this side always stays below the x-axis. You can analyze the sign of those sometimes too to help you figure out where it's at. So by that, what I mean is up here, when we get above, when this x gets above whatever that 2/3, then it would be a positive up there, below 2/3 a negative, and then on the bottom, when you get these two negatives down here, so if this is -4, this is -5 or whatever, -5, these will both be negatives. So then that would always stay below because you got two negatives to make a positive there, but the -5 up here would be a negative. So overall it'd be negative. So staying below the x-axis and above when you get further to the right. So in this final graph, see if I can draw this, we would have had this part in the middle that would have been way up. You know, this was, we said it was up at like 50. And then this one over here came out and across and then came back down, approaching the x-axis. And then over here, we had it where it came up and it stayed below the x-axis. So those would have been all the parts of that graph. So what are the three different possibilities that you have to be able to do for your horizontal asymptotes? Remember what we said before. We had, if you have the degree on top, like an x, and then down here an x squared. So when you go to infinity, that's going to have an infinity on the bottom. So that's going to be the x axis, or when y equals 0. And then we said if your degree was the same on top and the bottom, so if we have x squared, well, let's make it a little more interesting, like a 2x squared, and it equals the degree on the bottom. So if this was a 5x squared, these infinity parts that are your x's, it's like those would cancel out the x squareds here. So then your horizontal asymptote ends up being the coefficients, in this case, the 2/5 that I made up there. And then the other one is if the numerator has a higher degree by 1, so let's say we had a 3x squared up on the numerator and a 2x in the denominator. Now what you have to do is you actually have to divide it out. So I'd have to 2x into the 3x squared, and you get, it's really not a horizontal, although sometimes, you know, some people, it'll often be called, because it's a slant asymptote. So you might get a line that has to come in here and then it goes down the y-axis or something, or it comes along here and then it goes up along the y-axis. So you get these kind of slanted. They'll either be called a slant asymptote or sometimes they're called oblique. Kind of just depends. I think this book uses the word oblique, but seen it called both of those in different places. But for this one where the degree on top is larger, then you have to actually divide it out. If you can use synthetic, that's fine. If there's a remainder, you get to ignore the remainder, because remember, the remainder goes over this divisor, which has x in it, and we're going out to the infinities. whether it's the negative or the positive. So you'd have an infinity in the denominator, and anything over infinity is going to be 0. So you're going to be able to ignore the remainder if you have it. Just use the long division answer that you get and ignore that. And then you're going to have one of your x's into an x squared, so you're always going to have a linear term here. So whatever that number is, in this case, it would have been like a 2/3 or a 3/2. So, and I would have had that for a slope on that line. So those are the 3 horizontal asymptote possibilities that you have to watch out for. Well, let's try this one. So if we're going to graph this one, let's see, what do you want to look for first? How about we look for the horizontal asymptote, since we were just talking about that. Remember, that's the degree. So the degree on top, look at these highest degree terms, degree on the bottom, they're the same. So in this case, my horizontal asymptote is going to be y equals 2/3. Let's see, let's talk about the x-intercept. Remember, that's y equals 0. So when does a fraction equal, I wasn't trying to write there. When does a fraction equal 0? Fraction equals 0 when the numerator is 0. So when does 2x plus 1 equal 0? Negative 1/2. So my x-intercept at negative 1/2. How do I find the y-intercept? How do I get the y-intercept? Hopefully you would say the y-intercept is when x equals 0. So if you plug an x equal into 0 on the numerator, we'd have a 1. Over in the denominator, we have a negative 4. So my y-intercept's there. How do I get the vertical asymptote? So remember, first of all, you try to simplify if you can, because if anything cancels out in here, that makes something that's called a hole. Your graph's determined by the simplified version, but you look at the original one. If something canceled, then you have to also say x cannot equal what would have made the denominator 0, or the original problem wouldn't even exist. So vertical asymptote, denominator equal to 0 after you've simplified. Nothing did simplify here though. Set the denominator equal to 0, add the 4 to the other side, and divide by this 3. So my vertical asymptote, 4/3. So if we're going to get a sketch of this graph, again, let's see. I had a horizontal asymptote at 2/3. So if that's 1, 2/3 is down here somewhere. Horizontal asymptote. I had a vertical asymptote here at 4/3, so a little more than 1 if that's 1 there. So I've got a vertical asymptote at 4/3 right there. I've got an x-intercept here at a -1/2, an x-intercept at -1/2, and a y-intercept at -1/4. And so that is just helping me to know that one of my pieces of the graph is sort of like in here. And then the other piece, for past on the other side of the vertical asymptote, let's just say we put in a, so that was 4/3 right there. So let's say we put a 2 in. If I put 2 in, my numerator would be 4 plus 1, 5. And 6, 3 times 2 is 6. 6 minus 4 is 2, so 2.5. So 2.5 would be above this horizontal line. That was because that was up at 2/3. So that means that my other piece of this graph is up in that sector right up there. So there's how I would get a graph of there. Well, then they give you a story problem. So in this problem, they say in a city where there's air pollution, they've got technology to remove the pollutants from the air, but it's at a cost. So where P is the percent that you're trying to remove, 8.7 times P divided by 100 minus P, that'll calculate F of P, which is the cost that it's going to take, and it's in millions of dollars. So the question, first of all, is if we're going to graph this, if we were going to graph this, what's it going to look like? So for example, like a horizontal asymptote. Remember, that's the degree on top, which would be, you look at the coefficient, 8.7 P over a -1. So it'd be just the 8.7 over a -1. So I have a horizontal asymptote down at -8.7. So if that's -8.7, there's a horizontal asymptote down there. The vertical asymptote, how do we get that again? The vertical asymptote, remember that's when the denominator equals 0. So 100 minus P, when does that equal 0? When P is 100, right? So my x-axis here, that's like my P. And this is my millions of dollars. So this represented a -8.7 millions of dollars. So then, let's see, where was I at? My vertical asymptote at 100. So if that's 100, so then I've got this vertical, whoa, I'm not even headed for that. Down through there. And then where would the rest of my graph be? Well, if P is 0, so if I put in a 0 for P, I'm going to get a 0 because 8.7. So I got a point at 0, 0. And so we've got to, if there's a point there, then we've got to be in this sector approaching that asymptote. And also, oof, rough. And also approaching this asymptote. Now here, then if you're on the other side of the 100, so if you're 101 or something over here, if you were at 101, 8.7 times 101, that would be like 87. For 101, that'd be a negative. So that'd be a positive. So that must be in this segment right, heading out to that asymptote. And if I wanted to do a check on that, make sure my graph is right, that was 8.7 P over the 100 minus P. Let's just jump over there to a Desmos quick and put that in there. 8.7 P. And down on the bottom, 100 minus P. Except I probably need to put these as X's. Zoom out a little bit, might be able to see what those are doing. So this section down over in the bottom right, I think I have that in the wrong place. If we take a look, make sure I got my equation right, 8.7 P100 minus, yep. So let's go back, and this one over here was back down over in here. The last part of this question, it says, what percent can be removed for 78.3 million? My preferred way to do that would be to come back to Desmos again, put in a second equation that says 78.3 let's see, that'd be y equals when my cost is at. And I could just come up here and actually find that it would be 90. So what did the X represent, the percent? So 90%. So we could remove 90% of it for 78.3 million. You could try using some other calculations in that problem and do it algebraically, but I would just do that for this point. And how would you graph this one? So to graph this problem, the first thing that I would say is we got some factoring to do. I don't think anything's going to cancel, but if it did, it would be a whole. We probably should talk about one of those here before we finish this up. So if I had 2x minus 3, because these are the difference of two squares here. Oops, get that out of there. And 2x plus 3. And then this denominator looks like an x plus 5 and an x minus 3. To get that, 2x in the middle and a negative 15. So degree on top and the bottom are the same. So 4 over 1 gives me my horizontal asymptote. At y equals 4. When the degree on top and the bottom are the same, 4 over this would be like a 1 right there. Vertical asymptote, remember that's the denominator, equal to 0. Vertical asymptote. Denominator equal to 0, so when would this term be 0? When x is negative 5. It's really what x cannot equal, or you'd be dividing by 0. And then 3. So at negative 5, we've got a vertical asymptote. And at positive 3, there's a vertical asymptote. And then this horizontal asymptote was up at 4. Let's see, what about x-intercept? What about an x-intercept? Remember, that's like y is 0 on the x-axis, and the way a fraction equals 0 if the numerator is 0. Well, that would be when either 2x minus 3 or 2x plus 3 is 0. So when does 2x minus 3 equal 0? Add the 3 to the other side, divide by 2, that'd be 3 halves. And when does 2x plus 3 equal 0? Just the opposite of that, subtract 3 and divide by 2. So a positive 1.5, that's like in here, and a negative 1.5, which is in here. So then this piece of the graph is coming up. Well, I never did figure my y-intercept. Let's talk about that. Where's my y-intercept at? That might help get my graph a little more accurate. Remember, that's x equals 0. Plug a 0 in for x, and we have negative 9 over negative 15. 3 goes into each of those. So 3/5. So if that was 4, it's really just barely down here. So that means this comes up, goes over, and comes back down. And then it's going to approach that asymptote over there. Now, what's it doing on the right of 3 or on the left of negative 5? Because is it above the 4 or below? I don't know. Let's take a look. So let's put in a positive 4. That'd be over here, right? 4 would be 4 squared. Holy smokes, this is going to be some big numbers. Let me grab a calculator to help out with when we get to that big of numbers here. Let's see if I can find a calculator here somewhere. calculator. So I was about to say we're looking at, if we're at a 4, so that on the numerator would have been 4 times 4 squared, which is 64, minus 9. So in my numerator there, if I'm putting in that 4, it gave me 4 times 4 squared minus 9, all divided by 4 squared plus 2 times 4 would be 8 minus 15. So 16 minus 15 would be 1. That'd be all over 9, which comes out to just over 6. Which, if I'm over 6 there, that means that's above this asymptote. So now I've got a piece of my graph up here. And then I would do the same thing for if I had a point over here that was to the left of -5. So, you know, like -6. If I put in a -6 into here, I end up with 4 times 6 squared minus 9 up there is like 135. Over in the denominator, well, let's see, I can probably do that one. If I do it from the factored form, 11 times 6 minus 3 is 3, so that's be 30. 11 times 3 would be 33. So 135 divided by 33. Just over 4. So again, that would be up here. Well, and you know, just again to say, did I make an arithmetic mistake here, trying to run around, find a calculator and all that business that I was doing? Take that original equation, 4x squared minus 9 all over x squared plus 2x minus 15. You know, don't give up here. Let's figure it out. And jump over to Desmos again. Get rid of that equation. In my numerator, I had 4x squared minus 9. And in the denominator, I had x squared, shift 6 for the caret, plus 2x, and minus 15. And that looks to me like what we came up with, doing it all by hand on the other part of our graph. Now, the one last thing that I did want to talk about here was, what do you do? You've heard me say verbally, but sometimes if you end up with a problem where something cancels out. And so by that, let me make something up here. If we, let's say we factored our problem and we came up with x plus 2 times x minus 3, and it was all over x times x plus 2 times x minus 7. So our leading terms on top would have been an x squared, and on the bottom we'd have had an x cubed. So from that, we do know that we have a horizontal asymptote on the x-axis, for example, because we have a higher degree on the denominator. But notice, see, these two factors canceled out. The rest of our graph now is determined really from the x minus 3 over the denominator would really be x squared minus 7x. Or if you want to leave it in factored form, it's right there, x and x minus 7. But this x plus 2, x can still not equal -2, our original problem would have never really existed. So we've got our horizontal asymptote, our vertical asymptote. When does the denominator equal 0? You only use the parts that are left after for the vertical asymptotes. So it'd be 0. That's on the y-axis. Pretend that's on the y-axis. Totally missed it. So we got a vertical asymptote there, and then when does this one? So at 7. We'd also have a vertical asymptote. Okay, and then we still had that horizontal out there. We could get all of our other parts in here then. So let's see, x, when x is 3, we would be on our, y would be 0. So 3 is in between here somewhere. So we know we have a point in here. What's the rest of the graph doing in here? Well, we've already talked about all the rest of that, so you could find all the other points by picking points and finding it. I'm kind of curious. I didn't have a y-intercept, so I've got x minus 3 over x times x minus 7. X minus 3 over x times x minus 7. X minus 3 well, we can just do that as the x squared minus 7x. So it looks like that is the whole part, x minus 3 up above, down below, and it crosses in between there. So our graph, again, should look like this in between here, at that point that I just missed. And then wherever the other two parts, the other two parts are top right and bottom left. Top right and the bottom left. So then you had this one up here. You had this one over here. And the last thing was x cannot equal -2. So you got to go over here to wherever -2 is. You got to put a hole in your graph, and you got to put a little eraser to take out the inside of that. And that denotes that there's a hole or a break in this piece of the graph because of this part that reduced or simplified out. So you always got to kind of keep an eye on that because you can't really see that on the graph. Let me show you. If we go back to that Desmos and you look, do you see in here at the -2? Let's see what it looks like if I put it in, because I didn't even type it in here. We had an x minus 2 or x plus 2. If the hole's at -2. Add into here the x plus 2.